Hi guys, this is our Trig lesson 3 over the identities. We're going to talk about cofunctions, what those are, like what does it mean to be a cosine, cotangent, cosecant, and we're also going to talk about the sum and difference identities, and there's going to be a little music in this too, so bear with me and my horrendous singing voice. So um, I saw a little cartoon here. I thought you might get a kick out of it. If you know trig identities, it's funny as heck. If not, well, you do you. Uh, I'll leave it at that. So what are cofunctions? Well, sine and cosine are cofunctions. So let me just write down a couple of things. If I were to ask you, just using your unit circle, using your gang signs on your fingers here, sine of 30, I know, same as sine of pi over 6, it's 1/2. Likewise, cosine of 60 is also 1/2. So sine of 30, cosine of 60 are equal. I have some other examples here. Cosine 20, sine of 70, while they are not the same as like sine of 30 and cosine of 60, if you were to work these out, these are not ones that are good to do with your unit circle because they're not the special right angles, but you'll find cosine of 20 is the same as sine of 70. You'd also find that while it's different from these other ones up above, cosine of 50 is equal to sine of 40. If you don't believe me, try it out on your calculator, have a blast. And I know that sine of 3 is equal to cosine of 87. Sine of 1 is the same as cosine of 89, things like that. So what does it mean to be a cofunction? Like sine, cosine, cosine, sine, cotangent, tangent. What is the co? I guess we've done the graphing. We've seen how they're different graphing-wise. But I hope what you see is that the sine and the cosine can be equal when something happens with their angles. If you notice, if you were to add 3 and 87, that adds up to 90. 50 and 40 add up to 90. 20 and 70, 30 and 60. So I'm thinking of a word that starts with co that maybe I learned in a geometry class that says it starts with co and then it means angles that add up to 90. And that word is complementary. So when we talk about cofunctions, the co in cosine, the co in cotangent, the co in cosecant basically stands for complementary. So what does that mean? It basically means that cofunctions mean I have functions that are equal when their angles add up to 90 degrees, when their angles are complementary. So like basically the graph of the cosine has a complementary relationship with that of the sine. Sine of 10 is the same as cosine of 80. They're the same when their angles are complementary. Here are 3 what are called cofunction identities. You may want to write that into your little bag of tricks for your identities. Again, these are called the cofunction identities. Sine is cosine 90 minus theta. Tangent is cotangent 90 minus theta, and so forth. Secant is cosecant of 90 minus theta. Or if you're in radians, pi over 2 minus theta, like that. I want to take a little different approach at this. Let's think of like this in terms of graphing transformations, kind of like this. So I'm going to give you 2 graphs here. And if you look, again, these are just some screenshots from my calculator. Sine function is graphed in blue, cosine is graphed in red, intervals from negative 2 pi to 2 pi. I hope what you see is that the sine and the cosine are basically the same shape. If I were to take this cosine function, like right here, and shift it some little bit to the right, you'd see that basically they were the same graph. So basically, if I take a cosine and shift it to the right, specifically if I shift it pi over 2 or 90 degrees to the right, then your sine, they basically become the same function. So little thing, maybe this helps, maybe it doesn't when you're talking about your identities. Way at the beginning, I know that sine is the reciprocal of cosine or cosecant, so 1 over sine is cosecant. 1 over cosine is secant. 1 over tangent is cotangent. Those are the reciprocal relationships. The cofunctions, the ones that are the same when their angles add up to 90, is sine and cosine, tangent, cotangent, secant, and cosecant. So what I see is that tangent and cotangent are the only two that are both cofunctions and reciprocals of each other. So this is a little something I thought, well, maybe it'll help you guys out if you want. All right. Identity time. Take a few minutes, write these 6 down. There's some songs that go with them. They probably will embarrass my daughter. I don't care. So here's the idea. Sum and difference identities. Sum means to add, difference means to subtract. So this happens when I'm adding 2 angles, subtracting 2 angles, adding 2 angles, subtracting 2 angles, and so forth for both the tangent and the cosine and the sine functions. Generally what a lot of people have trouble with is memorizing the identities. So I'm just going to share a little bit with you here. One of my daughter's favorite habits when she was little, it's basically just annoying her parents. That was kind of her gig, and now that she's older, still same deal. But she used to sing like Old MacDonald for like ever. It drove me, like the whole Led Zeppelin Stairway to Heaven version that just never seemed to end. It went on for like days. And so you get a little sick of hearing Old MacDonald, and then genius happened. As she's singing that, I'm sitting here thinking, whoa, I can use that to help me memorize sine alpha plus beta. Allow me to help you out with that. So here, sine alpha plus beta, it goes something like this. Instead of Old MacDonald had a farm, it goes, Old Man Winter had a sine, cosine, cosine, sine, and it works again. Sine alpha minus beta, Old Man Winter had a sine, cosine, cosine, sine. The one thing you need to know, though, is these signs in the middle. I will tell you that when it's a sine, it retains its sign. So sine A plus B will be a plus. Sine A minus B will keep the minus. Next one, it's my daughter's, kind of watching me do my thing. She's like real little and running around in her diapers and stuff like that. And she's older now, but anyway, excuse me. She's like asking me what I'm doing, and I said I'm doing pre-calculus, and she says I want to learn, and I said no, you're like 1 or 2. It's not happening. So she started looking over my shoulder, and asked me to read what this was, and I said, well, this is a cosine, and a sine, and a sine, and doing what little children do. They repeat things over and over and over again until they drive their parents completely insane. Then started putting it to music, and this became the cosine dance. So for the cosine alpha plus beta or alpha minus beta, it became cosine, cosine, sine, sine, cosine, cosine, sine, sine, and I heard that for, I don't know, days. So I'm not likely to forget it, which if you're talking about cosine or if you're talking about trig identities, that's probably a good thing. But remember how we said here that the sine keeps its sign? The cosine doesn't. So if it's cosine A plus beta, then it's minus. Cosine alpha minus beta changes signs to be plus. There is a song from here. I only have so much video, and most of you probably never heard of it. It's kind of obscure, and I'm not even going to ride that train. Otherwise, you're going to have a really long video, and well, heck, you may have anyway. But tangent A plus beta starts off with tangent A plus tangent B on the top, and then over 1 minus tan A, tan B. Tangent A minus B or alpha minus beta starts off tangent alpha minus tangent beta over 1 plus tan A, tan B. So again, if it's tangent A plus B, it's plus on the top, different sign on the bottom. Tan A minus B, minus on the top, change it on the bottom. These are also some good identities to write down. Now we're going to do a few problems. Start with some easy stuff. Sine 60 degrees or sine pi over 6. I'm sorry, pi over 3, excuse me. And cosine 45, sine pi, that's cosine pi over 4. These, you don't need anything fancy. They're just on your unit circle. You can do the hand trick, your little gang signs. Those are easy. What's not easy? Ones like this. Ones like this. See, here's the problems with part B and C, or with C and D. See, we know these 60s, 45s, 30s, and their reference angles and stuff like that from what we've done, because they're the special right triangles. The problem is we don't have, we have a 30, 60, 90 and a 45, 45, 90. Those I can do or find exact values. Those I can calculate real simple. Problem is 15 isn't one of my special right angles. So what do? Well, I'm going to use two angles that I have. So I'm going to find a way to incorporate those special right angles. So I know I can write 15 as 45 minus 30. Then I'm going to use my identities. Remember we talked about sine alpha minus beta. Old Man Winter had a sine, cosine, cosine, sine, and then the sine keeps its sign. So if it's minus here, it's minus here. Okay. Alpha matches up with 45 degrees. Beta matches up with 30 degrees. So I just replace. So instead of sine alpha or sine A, I say sine 45. Cosine beta, well, beta is 30. It's cosine 30. Cosine A, sine B. Now, since we've converted the 15 into angles we actually do have in our special right triangles, now I can just use my gang signs here and my unit circle, and I know sine 45 is root 2 over 2. I know cosine of 30 is root 3 over 2 minus cosine 45, root 2 over 2, sine 30 is half. Then we multiply. Root 2 times root 3 makes root 6. And then on the bottom, 2 times 2 is 4. So my first fraction ends up being root 6 over 4. Minus root 2 times 1 is root 2. 2 times 2 is 4. So I get these two fractions, and kind of cool here, they both have the same denominator. So I can combine them, and I get root 6 minus root 2 all over 4. And no, you cannot subtract these or combine these. They're not like terms. You don't take apples and oranges and get bananas out of the deal. It just doesn't work that way. So we're done with that one. Okay. Now let's take cosine 75. Again, my special right angles are 30, 60, 90, 45, 45, 90. You may ask too, like in this problem, I chose to go 45 minus 30. Some might say, could I have gone 60 minus 45 for my A and my B? And yeah, so long as it makes 15, it would have worked out pretty much the same way. You'd have gotten the same answer, so no biggie. So you have some flexibility in how you do these. So here, I only know of two of them that either add or subtract to make 75, and that's if I take 45 and 30. If you want the 30 first and then the 45, it'll work the same. When you're adding, 2 plus 1, 1 plus 2, they're the same both ways, commutative property, you're fine. So then here, my identity for cosine alpha plus beta is my cosine, cosine, sine, sine. And then if this is plus, cosine changes. And then I just do a little plugging in. 45 is alpha, beta is 30. So cosine A is cosine 45, cosine B is cosine 30, minus minus. Sine alpha is sine 45, sine beta, sine 30. Do your unit circle. Cosine 45 is root 2 over 2. Cosine 30, root 3 over 2, minus sine 45, root 2 over 2, sine 30, half. You multiply, and wait just a stinking minute. I've seen that answer before. Let me go back. I'm pretty sure I saw, oh, it's the same answer I got for part C. That's weird. I wonder if that's a coincidence. When I say I wonder, it's not a coincidence. You might say, how did you know it was going to do that? I specifically wrote this problem so that they would have the same answer. Here's the idea. Remember we talked about cofunctions? Sine and cosine, meaning that the sine and its cofunction are equal whenever its angles add up to 90. And the last time I checked, 15 and 75 are complementary angles. They add up to 90. So basically, since the sine and cosine are cofunctions, or complementary functions if you want to call them that, their solutions must be the same when their angles add up to 90. So really, when we did part C and we found the answer to part C, I was done. I didn't have to do all this other nonsense to find that. I just had to use cofunctions. So kind of nice to know. Okay, let's do a little proof here. Example 2, I want to prove that 2 cosine x sine y is the same as sine x plus y minus sine x minus y. Now, again, remember we want to work on the ugly side, which definitely looks like this part right here. And I want to try and make it equal that thing that I've boxed there in the red. So, and again, it's a lot easier to turn addition and subtraction into multiplication than the other way around. So let's use some identities. So sine x plus y, remember that's my old man Winter had a sine, cosine, cosine, sine, and then instead of a and b, I have x, y, x, y. And since this is plus and the sign keeps its sign, it's plus. Then I have this minus here that stays. And then here, sine of x minus y. Again, old man Winter had a sine, cosine, cosine, sine. It's probably ignoring the annoying the daylights out of you right now. It'll help you retain this knowledge. So, help you retain the knowledge of your identities. So, all I did was use the sum and the difference identities to, I would say simplify, but actually I made them a little bit longer. It's a little bit more expanded, but I basically broke it down a little bit. What's cool about this? Well, I can distribute this negative into this first term and into the second term. And when I do, again, my first thing stays sine x cosine y plus cosine x sine y. This is going to change the sign. So instead of a positive sine x cosine y, it's now a negative sine x cosine y. And instead of a negative cosine x sine y, we distribute the negative, it now becomes plus. Why is that cool? There's why that's cool. Those are two like terms, one positive, one negative, they cancel. So I get 1 cosine x sine y plus another thing that's exactly identical to it, which means I have 2 of them, which is precisely what we're trying to prove. So, little cool stuff here. Okay, example 3. Use your knowledge of cofunctions, sum and difference identities to find the value of the unknown angle of a function. This is like that one where I gave you sine of 15 and cosine of 75. And if you work one of them, you can find the other really quickly in your head, just rather than reworking the whole thing. So I know tangent and cotangent are cofunctions, meaning these two are equal when the 73 and the theta add up to 90. So to find theta, I just take 90 minus 73 and 17. So in other words, tangent of 73 is the same as cotangent of 17. Using that same logic here, cosine and sine, again, cofunctions of each other, they're the same when their angles are complementary. So if I want to find what this theta is, I just take 90 minus this, and I get 71.6. So cosine of 18.4 is the same as sine of 71.6. Cool stuff. This one's really kind of neat too. Again, cosecant and secant, they're both cofunctions. they're also the same when their angles add up to 90 or are complementary. So cosecant of 45 is the same as secant of 45. So that's kind of cool here in that they're actually equal when their angles are equal. In this case, when they're both 45, they still add up to 90, which is why, like sine of 45 is equal to cosine of 45. Same thing, Or in other words, if you want to do it in radians, you could say sine pi over 4 is the same as cosine pi over 4. Now this one's going to probably give people a little more trouble because it's longer and weird. Let me make it unweird. Looking at it, it looks kind of miserable and crazy, and you say, I don't know how to find the cosine of 51 without a calculator, or the cosine of 32, or the sines of those. I can't do without a calculator. Don't feel bad, I can't either. But here's what I do know. I see cosine, cosine, sine, sine, cosine, cosine, sine, sine, which is an identity for cosine. And then since this is a plus, that would be cosine of alpha minus beta. My alpha being 51, my beta being 32. So this is the same as cosine 51 minus 32. So basically, I could simplify this whole thing down, this cosine 51, cosine 32, plus sine 51, sine of 32. It's basically the same thing as cosine 19. So kind of a nice way to simplify it down. Okay. Apparently I've lost the ability to count in that I did not do an example 5 here in my notes, or in an example 4 in my notes, and I jumped right straight to example 5. I am making a separate video for that because this is going to take a little more advanced work than what I want to just animate on a computer. So that lesson is posted on my webpage. It's uploaded on my YouTube page. So check that out. And then I left you some room here. I'm going to attach these slides and we'll go over example 6, which is, again, I skipped example 4 because evidently I can do pre-cal. I just can't add or count very well. We'll go over this one when we have our meeting, our online meeting. Okay? Hope that helps, guys. Bye.